What if I told you that we can determine exactly what a star is made of, even though the nearest one beyond our sun is over 25 trillion miles away? It sounds impossible, right? We can't touch stars, we can't send probes to collect samples, and we certainly can't bring them into a laboratory. Yet astronomers can tell you with remarkable precision that a star contains hydrogen, helium, iron, carbon, and dozens of other elements, sometimes down to fractions of a percent. This incredible feat of cosmic detective work relies on one of the most elegant tools in all of science: light itself. Every photon that reaches us from a distant star carries within it a detailed chemical fingerprint, a cosmic barcode that reveals the star's innermost secrets. The story of how we learn to read these stellar signatures is one of the most fascinating chapters in the history of astronomy. Our journey begins in the early 1800s with a German optician named Joseph von Fraunhofer. While studying sunlight through a prism, Fraunhofer noticed something strange. Instead of seeing a smooth rainbow of colors, he observed hundreds of dark lines cutting across the spectrum like shadows. These mysterious lines, now called Fraunhofer lines, appeared at very specific wavelengths and seemed to follow a pattern that no one could explain. For decades, these dark lines remained a puzzle. Scientists knew they were important, but they couldn't crack the code. The breakthrough came in the 1850s when German physicists Gustav Kirchhoff and Robert Bunsen, yes, the same Bunsen who invented the famous burner, made a revolutionary discovery. They found that when they heated different chemical elements in their laboratory, each element produced light at very specific wavelengths, creating unique patterns of bright lines in the spectrum. Even more remarkably, they discovered that these same elements could also absorb light at exactly the same wavelengths. When white light passed through a cool gas containing sodium, for example, the sodium atoms would absorb light at the precise wavelengths they would normally emit, creating dark absorption lines in the spectrum. This was the key that unlocked the stellar code. Kirchhoff and Bunsen realized that the dark lines in the sun's spectrum were caused by cooler gases in the sun's atmosphere, absorbing specific wavelengths of light from the hotter interior. Each element left its unique signature, like a fingerprint in light. Suddenly, the composition of the sun, and by extension all stars, became readable. The physics behind this process is beautifully simple yet profound. Every atom has electrons orbiting its nucleus at specific energy levels, like steps on a ladder. When an electron jumps from a higher energy level to a lower one, it releases a photon of light with a very specific energy and wavelength. Conversely, when light of that exact wavelength hits the atom, it can boost an electron to a higher energy level, removing that wavelength from the light spectrum and creating a dark absorption line. Think of it like a cosmic piano. Each element plays its own unique chord, with specific notes that correspond to particular wavelengths of light. When we analyze starlight with a spectrograph, we're essentially listening to this stellar symphony and identifying which instruments are playing. Using this technique, called spectroscopy, astronomers made their first shocking discovery about stellar composition. They found that stars are primarily made of hydrogen and helium, the two lightest elements in the universe. This was surprising because these gases are relatively rare on Earth, compared to heavier elements like iron, silicon, and oxygen. The Sun, for instance, is about 73% hydrogen and 25% helium by mass, with all other elements making up just 2%. But spectroscopy revealed much more than just basic composition. Different types of stars showed distinctly different spectral signatures. Hot blue stars showed strong hydrogen lines and very few metal lines. Cooler, red stars displayed complex patterns of molecular absorption bands from compounds like titanium oxide. This led to the development of stellar classification systems that organize stars by their surface temperature and composition. The most famous classification system uses the letters O, B, A, F, G, K, and M, with O being the hottest and M the coolest. Astronomers remember this sequence with the mnemonic, "Oh, be a fine girl, kiss me," though more modern versions have been suggested. Our Sun is a G-type star, sitting comfortably in the middle of this temperature range. One of the most remarkable discoveries came from studying the element helium. In 1868, during a solar eclipse, French astronomer Pierre Janssen observed a bright yellow line in the sun's spectrum that didn't match any known element on Earth. British astronomer Norman Lockyer suggested this line came from a new element, which he named helium after Helios, the Greek god of the sun. Incredibly, helium was discovered in the sun 27 years before it was found on Earth, making it the only element discovered in space before being found on our own planet. Modern spectroscopy has become incredibly sophisticated. Today's spectrographs can detect thousands of absorption lines simultaneously, allowing astronomers to identify dozens of elements in a single star. They can measure not just what elements are present, but their precise abundances, isotope ratios, and even the physical conditions in different layers of the stellar atmosphere. Advanced techniques have revealed fascinating details about stellar evolution. We now know that massive stars forge heavy elements in their cores through nuclear fusion, creating elements like carbon, oxygen, silicon, and iron. When these stars explode as supernovae, they scatter these newly created elements into space, enriching the interstellar medium and providing the raw materials for future generations of stars and planets. This process of stellar nucleosynthesis explains why older stars contain fewer heavy elements than younger ones. The first stars in the universe were made almost entirely of hydrogen and helium, the only elements created in the Big Bang. As successive generations of stars lived and died, they gradually enriched the galaxy with heavier elements. Astronomers call this process galactic chemical evolution, and it's directly observable through stellar spectroscopy. Recent discoveries have pushed the boundaries of what we can learn from Starlight even further. The Kepler Space Telescope and other missions have used a technique called asteroseismology, which studies oscillations in starlight to probe stellar interiors, much like geologists use earthquakes to study Earth's internal structure. This allows us to determine not just surface composition, but the distribution of elements throughout a star's interior. Spectroscopy has also revolutionized our understanding of stellar magnetic fields. The Zeeman effect, discovered in 1896, shows that magnetic fields split spectral lines into multiple components. By carefully analyzing these splits, astronomers can map the magnetic field strength and structure across a star's surface. Some stars have magnetic fields thousands of times stronger than Earth's, dramatically affecting their evolution and behavior. Perhaps most excitingly, stellar spectroscopy is helping us understand the formation and evolution of planetary systems. By measuring the abundances of different elements in stars, astronomers can infer what types of planets are likely to form around them. Stars rich in heavy elements are more likely to have rocky planets like Earth, while stars with fewer metals tend to have primarily gas giant planets. The precision of modern stellar spectroscopy is truly astounding. We can measure element abundances to within a few percent, detect the presence of rare isotopes, and even observe the effects of stellar rotation, magnetic fields, and atmospheric dynamics. All of this from light that has traveled across vast distances of space, carrying within it the detailed story of stellar composition and evolution. This remarkable ability to read the chemical composition of stars has transformed our understanding of the universe. We now know that we are quite literally made of star stuff, as Carl Sagan famously said. The calcium in our bones, the iron in our blood, and the oxygen we breathe were all forged in the nuclear furnaces of ancient stars and distributed through space by stellar explosions. Every time you look up at the night sky, remember that each point of light is broadcasting its chemical composition across the cosmos. Through the elegant physics of spectroscopy, we've learned to decode these stellar messages, revealing the hidden chemistry of the universe and our own cosmic origins. It's a testament to human ingenuity that we can determine what distant suns are made of, simply by carefully analyzing the light they send us across the vast darkness of space.